So hello everyone. Am I audible? So if you could confirm I'm audible, then we'll proceed. Right. Thank you. So today we will start machine learning, and specifically in machine learning we'll talk about supervised learning. And the slides I have prepared today in a hurry. So if you find some error, please point it out. Okay, there might be some errors. That is what I wanted to tell you. Okay. So this is the plan of today's lecture. We will talk about a brief introduction of machine learning, and mainly we'll talk about supervised learning. There are two broad um, categories of supervised learning. First is classification and the other is regression. We'll see what the difference between the two, and then we'll see the techniques of doing these two. Okay. So before proceeding, we should understand what is machine learning. So machine learning enables computers to learn from data rather than being explicitly programmed. So till now, what we have seen is we are specifically giving instructions to a computer to perform some tasks. But in machine learning, we don't give instructions. We actually make available data for the computer. And from that data, the computer tries to understand the relationships between the different features we are giving in the data. I'll tell you what are the features in the data, and then it can help us understand the data better and then make predictions and so on. So the goal is to recognize patterns and make predictions or decision based on data. Okay. So the key components of machine learning is data. So data is the main driving this machine learning concepts. It is the foundation for training and testing. We'll see what is training and we'll see what is testing. The algorithms, so the methods to identify the patterns and learn the data. So we have given access to this data, and we'll see what are the algorithms that are being used by the computer to understand this data, identify patterns, and understand what the data is telling us. Then we will also see what models are this algorithm based on. So we are giving some algorithms are just step-by-step instructions, but it is following some mathematical models. So we'll see the mathematical representations of the, and this is also talking about of the pattern learned. So sometimes we don't have much knowledge about the data, we just have the data. For example, if we collect data for animal voices, so if you can collect data and you want to try to learn, it will not be easy using machine learning. It may be helpful to use deep learning and neural networks to understand which voices are giving what response to the other animals. So if two animals are interacting with one another, understanding which voices are relating to what actions, those things come from here. So we are trying to access the patterns in the data. Okay, what are the applications? So spam detections. So we have emails and we can have spam detection. Some emails can be a spam or not, so we can have spam detection filters. We can have personalized recommendation like Netflix, Amazon, Google, etc. Self-driving car and many more applications are there. Okay, so what is supervised learning? You see, in supervised learning, in this type of learning, there are labeled data. So you have to have interference in the data. So for example, there are some features of the data. So if you're talking about say spam detection, so you can have some features like where the mail is coming from, what is the title of the mail, what words are being used in the mail, and so on and so forth. So those are features. So for example, you can say if um, lottery word is being used or not, so that can be one feature. How many times this lottery word is being occurred, that can be another feature, and so on and so forth. So you have features in a data, right? So if you see in an Excel sheet, you can have columns, and each column will be a feature. So one feature can be if that email comes from a trusted source or not, yes or no. Some can be count, so how many times the word lottery has been used, how many times the word subscription has been used, and so on and so forth. Those are the features of the data. The other label, the label which the human is providing, is if it is a spam or not, if spam or not. So we have to label that data. So these are the features it has, and we'll say, okay, if these are the features this particular email has, then it is a spam mail. If these are the features this email had, then this became a non-spam mail. Okay, so we have to label each and every email we have. So that data may have hundreds and hundreds and thousands of rows. Each row corresponds to one email, and we have a label whether it is a spam or not. Therefore, the supervised learning requires these labels. Okay. The algorithm predicts an output y based on the input x using examples of input output pairs. So this data which we are providing to the computer, they act as examples. So if this is the pattern we are seeing in the input data and output data is a spam, it is most likely that if the similar kind of patterns are seen in the next email, then it is more likely to be a spam. So these kind of patterns are recognized, and the algorithm predicts an output based on the input output pairs. That is why this labeling is required in supervised learning. So I have told you an email based on spam filters. You can, so over here we are doing classification. We are saying either that email is spam or that is email is not spam. We can also have linear kind of labels. For example, there can be features of a house. So if you are buying a house, there can be features is what is the locality of the house, how big is the house, what are the features of the house, for example, electricity, and what equipments are already there in the house, whether the house is furnished or not. These are the features of the house, and the label can be the price of that house. So this is also an input output pair, and this is also a labeled data, and therefore we will use supervised learning. So in this case it is categorization, so it is on off, or it can be multiple categories also. Over here we're just talking about two categories: spam, not spam. And the other is when the labels are continuous, right? So we are trying to get a value. Okay. So categories of supervised learning: first is classification, predict discrete labels. So it can be binary or multi-class, and or it can be a regression where we are predicting a continuous value. Okay. So we'll see only these two. So we are talking about just supervised learning in this lecture, and we'll see both of these, how algorithms are being used to do classification and then to do regression. Any questions? Okay. So supervised learning workflow. So what it does is we have to first provide the data, we have to collect the data, and what is so collection of data is first thing. We have to gather raw data and from a reliable source. Then we have to do pre-processing. We have to clean and prepare the data. So when you are, so these are fundamentals of data collection. When you collect data, there might be some mishandling issues, or some data might be missing, or so on and so forth. So there requires some pre-processing. And then obviously in these two things you have to label the data. So we assume that in data collection we are labeling the data itself. So whenever we collect the data, for example, the features of a house, we already label the data that this is the price of the house. So that labeling is already being done at this stage when we are doing the data collection. Pre-processing is done. Then we do split data. So what we do is we split the data into a training set and a testing set. Okay. For now, we will not talk about validation. We will come to validation a little later. So we will just split the data into two groups: a training data and a testing data. And we will train the model on this training data. And after we have trained the model, we will talk about what does it mean to train a model. Then we will test that model on our testing data. And after testing the data, we will be able to tell how good is our model, if it has a high accuracy or not, what is the accuracy, what is the precision, and so on and so forth, right? So we split the data into training data and testing data. If you don't do so, if you try to train the model in whole complete data, then you will have some issues which we'll also talk about in this class. Okay. So what I'm saying is, if you don't split the data, you just train the model in the entire data. First thing is, you'll not have anything to test, right? You have already trained in the whole data. You cannot tell how good is your model, right? Another issue which comes is, you see, you are taking the complete data you have. So what might happen is your model is very good at your training data, but it might become very, very bad in the predictions. So we will see how can this happen and when this happens. So I'm saying the model will be very fit for your data, whatever data you have, but when you try to use that model to do predictions, it gives very poor results. This might happen if you don't split the data into two groups, a testing data and a training data. Okay, we will see. Okay, then we will train the model, fit the machine learning model, and to the training data. So we will see what does it mean to fit the machine learning model. Okay, we will see what it means. Validation we are leaving for now. Evaluate model. So over here we will perform model's performance. We will test the model's performance. We will evaluate how the model is performing, and then we will deploy this model. Okay, so this is just an overview of how we do supervised learning. Now we will talk about the two broad supervised learning categories. The first we will talk about is classification. Okay, so what I'm doing is, first I am just presenting both together. I am saying this is classification and this is regression, such that you can differentiate between the two. Then we'll proceed to talk about only classification, and then later we will only talk about regression. Okay, so first we'll talk combine both of them and then see the differences. So over here I'm saying introduction to both classification and regression. Supervised learning problems are broadly categorized into two classes. One is classification and one is regression, where classification is just discrete labels and the regression is continuous labels. Both technique map input features to output Y. So we have talked about some examples, what are input features and output labels we want. Okay, we have to choosing between them depends on the nature of the target variables. So you see, one specific data can have classification problems as well and regression problems as well. For example, that house problem we were talking about. So we can have one data set which talks about houses in a area, or not a area, or in a state maybe. Okay, so it can have uh, features like what is the size of the house, what is the locality of the house, and more labels, not labels, more features we can have in that data. The labels can be of two different classes as well. So it can be either of classification, it can be either of regression. So for example, when we are talking about classification, then what we can have labels as, we can have high cost house, or low cost house, or medium cost house, something like that. This is classification problem on the same data. Another is what is the price of the house, exactly what should be the price of the house. This is a regression problem, right? So you can have different kinds of problems in the same data set. That is what I wanted to tell you over here. Any doubts? Okay. So we have just talked about this. I'll just skip. What is classification? A task where output variables is a category of classes. Characteristics are outputs are discrete and finite. Examples we have seen. Okay. What is regression? This is also we have seen. The task where the output variable is a continuous variables. Key characteristics are the output are numerical values within a range. Examples we have seen. Okay. Yeah, so these are just skipping. Okay, now this is important. We are visualizing what is happening. So you see, I am saying the features is only one. So for this example, I'm saying only there is only one feature. You can have multiple features. You can have 2D features, 3D features. When I say 3D features, it means three different features, four features, five features, n number of features. But for this case, I'm just saying, suppose the input has only one feature, and this is for a different problem set. This is for a different, not problem set, data set. This is for a different data set. So first we'll see for classification. You see, when this was the output, sorry, when this was the input, then the classification labeled is at labeled it as red. So it can be high costing house and low costing house. So when this was the input, we are saying that it is a high costing. Just a minute, it is not a 1D data, it is actually 2D data. So this is actually 2D. So I have labeled it incorrectly, that's why I'm saying. And again, I'll reiterate. So I have made this in a hurry, there can be errors. Okay, so this is input 1 and this is input 2. Okay, So x-axis is input 1, y-axis is in input 2 for the first case. I'm just talking about the classification problem. All right, I'm just talking about this problem, classification problem. So it has two features. Now when the features input 1 and input 2 are this, then the label is red label. Similarly, when the input 1 and input 2 is this, then the label is blue label. So it can be low price or high price. Okay. And similarly, all the different data sets are plotted over here. Now the task of classification is to separate the data into groups such that if you have new data, then you will be able to label it as a high price house or a low price house. For example, if it is a the data set of prices of a house, so you can just think of one classification, that this is one classification. You are saying that this line divides the two groups. One is a low price house, one is a high price house. So this works well, right? You see, whatever data you currently have, you can just see it, it classifies properly. And by the looks of it, you can say that this is a good model, because if you have a data over here, you can pretty much with good probability, you can say that this is a red dot, right? Over here, if you have a data, you can just say, okay, because we have a model like this, so this is the model. This line we are talking about is the model. We are trying to get this line which separates the data. If we have a data like this, then we can say, because the model is there and that model is predicting that it is a blue dot. Okay, so this is how we can do. Now you see, this is not just one model you can build. So this is model 1. You can have multiple different models. So for example, you can have a model like this, right? Like this. Okay, so this can be another model. You can have a model like this as well, right? Not this, something like this. So you see, you can have multiple different models for the same problem, and using different algorithms to build the model, or not algorithms, different mathematical concepts to build the model will give you different line over here for this problem, different lines. Okay, and you see, suppose we are talking about this line. So we are talking about this line, and now you get this point. This point you get, right? With this model, you will have to, that model will predict that this data is a blue dot. It will not predict that it is a red dot. You can see that, right? It is saying that this side is the blue area, this side is the red area. But seeing this, you can see that this is not a good model, because it seems that this should be a red dot, not a blue dot. So these are the things you have to take care when you present a model. Okay. So when we draw this kind of line, this is known as perceptron learning model. This is a perceptron model. We will see the different models we are talking about. Okay. But the idea is you can have different models for the same data sets. Some models can be better than the other. Okay. Any questions? All right. So this was for classification. Now we will talk about regression. So for this regression, we have only one input. So for classification, we had two inputs, but for regression, the way I have drawn this diagram is for one input. So it has only one input. If the input is this, the output is this. If the input is this, the output is this. Okay. So we have plotted the different data sets. Now the idea is to get a line which best fits the data set, such that if you get one more input, so suppose you got this input, this as the input, because you have only one input, so this will be the input. Now you can just go to that line and you can predict what should be the output. Therefore you can say this will be the output. Okay, so this is how we will use regression to predict. And again, you can see that this line is very important. How you plot this line governs what will be your output. You can have a linear line, so this is a linear line. You can have a curved line as well, and you can increase the complexity, and then the model may become good or bad. We will have to test it on the testing data. Is that all right? Any questions?
Shubham,
Yes.
uh, does that mean classification requires at least 2D data and regression requires at least one-dimensional data?
No, 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 no. Classification can have 1D data as well. So for example, this is a classification problem and I'm saying this is one or blue or red because we are talking about, so this is blue and this is red and this is the input. Okay. So if this is the input, so these are red. I'll just say like this. These are the inputs we have, right? And for each input, I can have a red dot or a blue dot. So suppose this is red, and this is red, this is red, and this the remainings are blue. Okay, so you can have a classification data where the input is only one dimension, and classification can be done. It can be of n dimensions as well. Is that all right?
Okay. Uh, Also, regression can have n-dimensional data.
Yes, yes. Regression
Okay.
has a
Okay. Okay.
but the way I have drawn over here is this side is the 2D input and this side is the 1D input. Okay. All right. Now we will see classification algorithms. So over here, I have just listed down the algorithms: K nearest neighbor, support vector machine, and logistic regression. We will not talk about this in detail. We will see when we talk about the algorithms for regression. Okay, so these are the different algorithms. Classification can have K nearest neighbor algorithm, support vector machine, logistic regression. There are decision tree as well. More algorithms are there. I have listed down three. So these are the algorithms that can be used to perform classification. Regression algorithms, linear regression, polynomial regression. Again, decision tree can also be used for regression. Okay, so these are the different algorithms for regression. Application of classification and regression. So again, it is very simple. When you have categories, then you have to use classification, and when you have to predict a continuous value, then you have to do a regression. I have given some examples: medical diagnosis to identify whether a tumor is malignant or benign; fraud detection, identify whether a credit card transaction is a fraud or not; image recognition, whether to classify an object in the image. So for example, you are showing Google Lens an image of a animal. It can classify that into different animal classes, right? It is a dog, it is a cat, it is a mouse, and so on and so forth. That can also be a classification problem. Regression, real estate, predicting house prices based on locations, features, etc. Finances, forecasting stock prices, trends, and so on and so forth. Energy, estimating energy demand based on the historical data. And there are many more applications. These are just few examples. Okay. Now we'll talk about the nearest neighbor classification. So from now, we are just talking about the algorithm used to perform classification task. Any questions? Okay, so this is a very naive algorithm, nearest neighbor classification. What it does is, first we'll see what I have written here: assigns a label to a new observation based on the closest neighbor in the training data. Okay, so we'll see. So for example, so I have just drawn two points. We can have multiple points. So these are the red points, and these are the blue points. Okay, so these are the red points and these are the blue points. I hope both are distinguishable. Now, this nearest neighbor classification algorithm tells you if you have, so what you have to do is you have the data set with you. Now, when you're trying to predict, what it says is where that point lies, you have to check what is its nearest neighbor, and then you label that data as that class. So for example, if you're trying to predict this point, so you see it is closest to a blue point. So it is first one neighbor classification. It is actually one neighbor classification. So the only the closest neighbor will be checked. So you see the closest neighbor is a blue neighbor. So we will label this dot as blue. Again, if you're talking about this point, this is the new observation, and the closest neighbor is a red dot, then you will say it is a red class. Uh, So we are predicting now, right? So it is red. The label is red. Now you can see that this has some problem. This nearest neighbor classification has some problem. For example, for this data set, you can see that the area for blue is somewhere over here like this, and the area for red is somewhere like this, right? Right? You see, if you get a point over here, or maybe not here, over here. So you see, it seems that it is a blue dot, right? It seems that it should be classified as blue, but its nearest neighbor is a red dot. And in such case, it may be mislabeled as red point. So this is one issue with nearest neighbor classification. Because you can have outliers, right? When you are collecting data, you can have some errors in the data. So this red may be an outlier. This red I'm talking about. This red may be an outlier. And that is giving you errors in your predictions, right? So this is one issue with nearest neighbor classification. Any doubt? Okay, so we are improving this algorithm because we see that this is not a very good algorithm. So next is k neighbors algorithm. So when we come back, you see k nearest neighbor algorithm. So instead of just checking the first nearest neighbor or the only one nearest neighbor, over there that k value was 1, therefore we are just saying nearest neighbor algorithm. You have to check k nearest neighbor algorithm, and then you have to count how many of them belong to which class. So for example, if we are talking about these points again, so I'll erase these points. So this is, I'll erase these points. Okay, so you see, when we are talking about this point right now, this point, what you have to do is you have to see k. Suppose we are saying k is equals to 5. You have to see the 5 nearest neighbor it has. So maybe I'll just erase this one also. This was not there. So maybe this is the nearest, first nearest neighbor, the second nearest neighbor, the third, the fourth, and suppose there are more dots over here, and we have counted 5 neighbors. Now you have to count how many of them are blue and how many of them are red. So you see over here 3 is blue and 2 are red. Therefore you will label this as blue point and not a red point, right? So this is how k nearest neighbor algorithm works. It checks, if you increase k, then your complexity increases. You have to add so many number of points, but your accuracy improves. There is one more issue. Increasing k can give you overfitting. What may happen is when you are trying to expand your, so what you're trying to do when you're increasing k, you are trying to expanding your area of neighborhood, right? When you're doing so, it might become too big. If that becomes too big, then it is an issue. Your prediction will not be good. So you can say that k is 100. In that case, you are just going very far away from your where you are, and you're counting 100 neighbors. It might not be very good. So finding a good value of k in that case is also a question of modeling. What should be a good value of k? Okay. So I hope you have understood k nearest neighbor algorithm. I can just go back again and tell you, so it is better. All right. So I'll just tell again. So what it does is whenever you get a point to predict, it has to check which is the k number of neighbors which are closest to it, and then it checks which are blue and which are red, and then it predicts that value which is more in the count. All right. Now over here you see, to get the k, so suppose when k is equals to 5, to get the 5 closest neighbor, it has to obtain the distance from its position to all other points, right? So if you are over here, to get the distance, I mean to say, to get the closest 5 neighbors, you have to know the distance of that point to every other point, and that is expensive, right? You have to obtain the distance from this point and this point, this point and this point, this point and this point, this point and all other points. Then only you will be able to know which are the 5 closest neighbor. So this is one drawback of this k nearest neighbor algorithm. You have to obtain, but you can circumvent this. This can be tackled by using better data structures. You can keep data and then use it after iterations. So those can be tackled, but if you are just implementing a very simple k nearest neighbor algorithm, then you might just calculate the distance between your point to every other point each time, and that may be expensive. So you have to modify your algorithm such that it improves the running time of the algorithm. Okay, is it all right? All right. Okay, so this we have talked about k nearest neighbor algorithm. Then we'll talk about perceptron learning. So you see, when we were talking about this diagram, I was not talking about k nearest neighbor algorithm. I was just drawing a line which separated the blue regions from the red region, right? I'm just saying this is the blue region, this is the area where
Shubham,
blue. Yes.
have you changed your slide? Because I right now I'm seeing nearest neighbor classification slide,
Yes,
and
I have.
you is freezed. I can only hear your voice. Is it the case with all the teammates?
Jairaj, actually, I can see my slide change. I have a laptop over here. I can see that my slide has changed. So I guess the network issue is from your end.
Yeah, I guess so.
Okay.
Please continue, but I can hear you.
Okay. So I was saying, when we were talking about this classification and regression, I drew a line, right? I said that this is a model which demarcates the area of blue region and red region. But when you are talking about k nearest classification, we did not draw any line. We are just saying find the k nearest neighbor, and then you will be able to identify the label of the new point. So this perceptron algorithm tries to obtain a boundary, the boundary which separates the blue region with red region. You might not be able to separate exactly, you may have some outliers, but nevertheless you are trying to get a boundary of the red region and blue region. Okay, so this perceptron model tries to get a curve. So the easiest is to draw a linear curve, that is a linear decision boundary. So what is perceptron learning? A method of binary classification. So it is a binary classification, two categories, by learning a linear decision boundary. So it draws a line that demarcates the area of the two labels in classification algorithms. It analyzes the entire data sets and create a boundary to separate the classes. For example, classifying weather conditions. The inputs can be humidity and pressure, and the output can be yes or no. So that blue line and red line, the blue dots and red dots, yes, it was rainy, no, it was not rainy, and so on and so forth. Classification is based on the side of the boundary the data point falls. So we will draw a line, and this one side will be yes and the other side may be no, or vice versa, right? So you see, when you are trying to obtain a line, you have to obtain. So for example, in this problem, we are having 2D, right? So this is input 1 and input 2, then it will be a line. But if you have n dimensions, then it is not called a line, then it is known as hyperplane. So if it is in 3D, you have three inputs, it will be a plane, right? It will be a surface that separates one area from the other area. If it is 4D, then it will be a hyperplane. In n dimension, a line is actually a hyperplane. Or the other way around, in 2 dimensions, a hyperplane is a line. In 3 dimension, a hyperplane is a plane. I hope I was able to convey the idea. So a hyperplane is a term which is used synonymously of what a line is in 2D, a plane is in 3D for n dimensions. All right. It is a hyperplane in n dimension. It is that plane in n dimensions which separates the region into two groups. Okay. Is that all right? So if you have a line, you will have x1. So a1, so I'll write w1 maybe. So a line, a two-dimensional in a 2D is written as w1 x1 plus w2 x2 plus w naught is equals to 0, right? This is how the line is written in 2D. Now for n dimensions, you can have n number of variables. So w1 x1 plus w2 x2. So I'll write w naught over here plus w3 x3 plus dot 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 wn xn is equals to 0. So this is a hyperplane in n dimensions. Okay, so this is how the equation of a hyperplane is written. If you remember, the equation of a plane is written as w1 plus w0 plus w1 x1 plus w2 x2 plus w3 x3 is equals to 0. There are three x variables, and in this machine learning, whenever I write x are the features. Okay, x are the features, and this perceptron learning tries to identify these w's, right? It is trying to obtain the weights, it is trying to obtain the coefficient of x's, what should be the value of w0, w1, w2 and w3. If it obtains that, then it actually defines that line. When you obtain these, so for example, for a line, if you obtain this w0, w1 and w2, the line is well defined. So this model tries to obtain that w values. Okay, and again, this is for equals to 0. So when I am saying equals to 0, we are talking about that line. But when I am saying this is greater than equals to 0, it is talking about the one region. And when it is less than equals to 0, it is talking about the other region. So if you remember, in linear programming, we had equations like this: a1 x1 plus a2 x2 is less than equals to b1. So it was talking about one region of one side, right? So if you draw the line like this, it is either this side or that side, one side. So whenever I write inequality, it is talking about one side of that. It can be a line, a plane, or a hyperplane. So for this as well, you can have greater than equals to 0 and less than equals to 0, or one equality can be omitted. So you can just say greater than equals to 0 and less than 0. Is that all right? So you are trying to understand this, right? So when I'm going in this area, so when I'm saying this side, then it is whatever the equation of the line, it may be greater than equals to 0, then it becomes this line, less than equals to 0 becomes this line, this side. Okay, so that inequality says which area you belong to, either this area or this area. Is that all right? If you're not able to understand, please stop me. I'll just explain again. Okay. Okay, so this is what the decision boundary is all about. So you see, what is this perceptron learning? We know that this will be the form of that hyperplane. So this is for a two dimension, x1 and x2, and for two dimension, that equation will represent a line. So over here, this is a line, right? A straight line. What does perceptron learning does? It tries to obtain the value of w0, w1 and w2. That is what it tries to do. And once you have obtained this w1, w0, w1 and w2, then you can just do predictions. You can say, if you obtain this value, so suppose what are you doing is, this is the equation of the line. You can say, so the function I'm saying, this is equals to h of x. So h of x1 comma x2, what is this? So h of x1 comma x2. So you input, so this is a function, you input x1, you input x2, the output will be h of x1 comma x2. That is, it will either be blue or red. So you input x1, you input x2, the output will be h of x1 comma x2. This is the function, right? This is what we want to obtain. So this function will be either 1 or 0. So it can be 1, we can just say it is rainy, and 0, it is not rainy. Or we can say other way around also. We can say 1 is not rainy and 0 is rainy. So this function, how it is defined? It is defined as if w0 plus w1 x1 plus w2 x2 is greater than equals to 0. If this happens, then h of x1 comma x2 is equals to 1, and then otherwise 0 otherwise. Okay, so this I have written incorrectly, this shouldn't come here. Okay, so this is how it is defined. Actually, if I write like this, it is actually not this, so I'll just rewrite this line. This is not how it is written. I have missed one point. It is written like this: h of x1 comma x2 is an indicator function of w naught plus w1 x1 plus w2 x2 is greater than equals to 0. So what indicator function means is, indicator functions means whatever is inside the indicator function, if it is true, then that indicator will be 1. If it is false, then the indicator will be false. So you see, when this value is true, that is w naught plus w1 x1 plus w2 x2 is greater than equals to 0. When it is true, then the overall value of this function will become 1, and therefore h of x1 comma x2 is 1. And when the inside part is false, then the indicator function will give 0, and then h of x1 comma x2 will become 0. So over here, while I was writing, I forgot to write that indicator. So this is just indicator of that, and the indicator is written like this: h of x1 comma x2 is equals to 1 if this is greater than equals to 0 and 0 otherwise. This indicator is same as like this. So overall, the idea is you are trying to obtain this function. How will you able to obtain this function? These w1, w2 and w2, if you obtain that, then this function is known, because these are the parameters of this function, right? You see, w0 w1 w2 defines that equation, and then when you have x1 and x2, you'll be able to say what is the indicator, what is the label, whether it is blue or red or rainy or not rainy. Is it clear, or a lot of mathematics is coming? You can just tell me, I'll just skip some mathematics and just go to the idea. Okay. Okay.
Excuse me, sir.
Yes, yes, Satya.
Sir, I didn't understood about the indicator function. Uh,
Okay, so I'll just help you understand. You see, how does an indicator function works? It is in mathematics, by the way. What is an indicator function? It is like this. I'll use another color maybe. It is like this. So this is the input I gave it. So the input is w0 plus w1 x1 plus w2 x2. You see, when you have these values w0, w1, w2, x1, x2, this will evaluate to one value. It will be one value, one integer. मतलब कुछ भी हो सकता है, 1 2 3 1.5, not integer, real value. So when you evaluate this, it will give you one value. If that value is more than, suppose this is 0, if this value is more than 0, then this function will become 0. You see, this is 0, this is 1, this is suppose 1.1 and so on, this is 0.5. So this is that function, h of h is the function, right? So indicator just says it can be either 0 or 1. When will it be 0? When this value is less than 0. So I have drawn it the other way actually, so it should be the other way. This is how it should be drawn. Okay, so it means when this value is less than 0, then the line is like this, that is y value is 0. When this value is more than 0, then this is the value. It is a step function. Indicator means उसके अंदर में जो भी है वो अगर true है, so what I am putting in
okay.
inside the indicator function, I'll just tell you once more, give me one more time. So if I say indicator is written like this, okay, so if I say whatever it is, so yeah, over here I am saying w0 plus w1 x1 plus w2 x2 greater than equals to 0. So whatever is inside it, if it is true, then that indicator will become 1, and whatever is inside that function, if it is 0, then if it is false, then that indicator will become 0. So it just indicates कि अंदर में true है कि false है. Okay,
Okay, yes.
so that is how we are using it to categorize कि false है कि true है. So I'll just show you over here. Okay, इसे भूल जाओ, अभी I'll just show you कि how it is being done. So you see, this is the line which we are trying to obtain, the equation of this line. It will be something like this: W naught plus W1 x1 plus W2 x2. If you have these values W naught, W1 and W2, then you can take any point x1 comma x2. You can take any point. So this is x1 and this is x2. Now you plug this value in this equation, and what you will see, so this is suppose so this side is suppose less than equals to 0. So if this value, if you plug this value over here, if this comes out to be something like -3, then you are in this side, and you can just say it is rainy. And suppose you are trying to get x1 comma x2, this value, so this is x1, this is x2. If you get this value, you plug it over here, you get some positive value. Suppose you got, by this equation you got 5, and since it is 5, then you can say that it is more than equals to 0, and therefore this side is that area, and you are at a no, not rainy day. So whenever I write like this, sorry, whenever I draw a line and I mark the areas like this side and this side, then what happens is, so W1 plus W0 plus W1 x1 plus W2 x2, suppose this is greater than equals to 0, and W0 plus W1 x1 plus W2 x2 is less than equals to 0. So अगर ये वाला evaluate हुआ है negative, then you are in this side of the line, and if it evaluates to positive, then you are on this side of the line. I'll give you one example so it will be better to understand. So suppose you have an equation, say 3x1 plus 6x2 is less than equals to 3. So over here, what is this? W1 x1 plus W2 x2 less than equals to W0. Okay, this is what you have. W0 is 3, W1 is 3, W2 is 6. Now you are trying to plot this line. कैसे plot करते हैं? You take the intercept form. So ये 3 को नीचे ले जाओ. So 3 by 3 x1 plus 6 by 3 x2 is less than equals to 1. So this is the intercept form. You just plot it. So over here, suppose this is 1, so it will be over here, this is 1, this is 2, because this is 1 and this is 2, so this is 2, and you draw the line joining these 2 points, 2 and 1. Okay, so this is the line. Now you see it is less than equals to 1. Now what you do is, this is 0 comma 0. So you see 0 comma 0 satisfies these equations or not. You see, when you say 3 into 0 plus 6 into 0, what is this 0 which is less than equals to 3? This is true, right? So this side is 3, this is true. Therefore you, when I say this line is less than equals to 3, I am talking about this area. So therefore this area, this region is what? This region is 3x1 plus 6x2 is less than equals to 3. On the other side, this region will become 3x1 plus 6x2 is greater than equals to 3. So equality आप remove कर सकते हैं, because equality means it is on this line. You can just remove the equality. Okay, so these are the two areas I'm talking about, right? Satya, is it okay?
Yes, sir.
Okay.
Thank you.
No, but
Yes.
but what shall be the value on the line? It has to be 0.
So when we are talking about this line, the equation becomes 3x1 plus 6x2 exactly equals to 3. So when
Okay,
you,
exactly. Yeah. Okay, got it.
okay, now now so we have understood how we can divide the both sides. Now we have to see how will we obtain these values W0, W1, W2. That is what machine learning comes. Okay, अभी तक हम लोग जो भी बात कर रहे थे, that was mathematics. Now we'll see how we'll obtain these values W1, W0, W1, W3 for 2 dimensions. For n dimensions it will be Wn. So W1, W2, W3, W4, Wn. Okay, so we'll see that. Okay. Okay, so what we'll do is, we will say that we have input and output data, right? So we have input data like this. Suppose input 1, input 2, input 3, input 4, dot dot dot, input n, and we have the label. So we will say this is x1, this is x2, this is x3, this is x4, and this is xn, and this is y. Okay. Now we have training data. So some rows are training data, some rows are testing data. So these are training data, these are testing data. Now what we will do is we will obtain the learning rule. So what we'll do is we will first say we will start with some weight. Suppose we can start with any weight, 1, 2, any weight we can start with. So we will say we are starting with w naught plus w1 x1 plus w2 x2 plus dot 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 wn xn is less than equals to 0. We will start with any weight. It can be 0 as well, by the way. You can start with 0. Now what you will do is we'll use this equation. We will say, so when I have written I, it should be subscript I, superscript I. I'll tell you what superscript is. So what I will do is I will say initially I am starting with all so from 0. So in the first iteration, 0th iteration I am starting. Now for the first iteration I will use the first row. So for the first row I will update w I. For first iteration it will become wi for the 0th iteration plus, so जो भी 0th iteration में था उसका value plus some update. So in each iteration for each row I will update each w. So इस iteration में I'll update w0, w1, w2, wn, फिर again इस iteration में I'll update, again इस iteration में update. So it is learning from the data. Initially it is saying कुछ भी से start कर लो, but as you see more and more and more and more data, you update your weights thoda 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 karke, and you will eventually reach to a point where your weights are accurately depicting, not accurately, somewhat depicting your true labels. Okay, so this is how we'll update. We will say wi, matlab agar wi is 1, so suppose we'll say w1 जो पुराना था w1 not. So subscript is for iterations, okay, and the lower one, so superscript is for iteration. This is iteration number. This is this कौन सा वाला weight है, okay. So this is equals to the पुराना वाला weight plus some change. क्या change? You see, we have the original label. Testing data में we have that label. So we will say y minus what we have predicted. So h of x जो भी हम predict किए और जो एक्चुअल में था उसका डिफरेंस मल्टीप्लाइड बाय सम फैक्टर अल्फा. आई टेल यू क्या है. जैसे मान लीजिए कि दिस वाज द इनिशियल इक्वेशन एंड आई हैड प्रिडिक्टेड 1, बट सपोज द लेबल वाज 0. I had predicted 1 but the label was 0, so it will be 0 minus 1. You see, this is negative, so this is negative, so this weight will decrease, right? So when the weights are decreased, this 1 will try to become 0. So we are trying to update it. And on the other way, if suppose this value was 1 and we had predicted 0, so what it will be 1 minus 0. So you see this is positive. So we are adding something to the weight. We are adding some part to the weight, right? So this difference is the error. This is the error. What is the original minus error? So this is what? New weight. So W new is equals to W old plus alpha times the error, right? So error times alpha, alpha एक factor rate, this is known as the learning rate. It should be very small, 0.01 or 0.02. This is known as the learning rate. What is the rate you want to learn your data? So you have to select this. It is actually small value, 0.1 or something like that. So you update your new weight considering what is your old weight plus alpha times the error. And this is how your new weight will be updated for each row. Dhire 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 it will converge to a value. And when you have converged to a value, then you can start doing the testing, and then you will be able to say how was your predictions. So this is how you update the weights. Is it all right? Others, is that all right? Okay. So this is how the learning rule is. So wi, so this I we can say that it is that I, which value it is, and we can just ऊपर में हम लोग लिख सकते हैं new and this is old. So w new is equals to w old plus alpha times alpha is the learning rate times the difference in the y values y minus hi times xi. यहाँ पे xi लिखना भूल गया था मैं, it should be times xi. Okay. So this is how W's are updated, and when you have many number of rows for testing, then so the more number of rows you have for learning or training, the better your algorithm becomes. So what you have to do, suppose you have 100 number of data sets, then you can just divide 70-30. So 70% of the data you can use for training and 30% of the data you can use for testing. So 70% of the data may your weights will be updated, and when we will test, we will see how we test the data. By the way, we will see that, and that will give you the accuracy of the model. If your model accuracy is not good, then you can increase the total number of data. Suppose you are saying 100 number of data से शुरू कर रहे हैं, then you should ask नहीं 100 number of data is not enough, start with 200, then it will be 140 and 60, right? So the more data you give, the more better your prediction becomes. And that is why machine learning and these neural networks, this requires a huge amount of data. Okay. And moreover, if you see, if your prediction becomes same as y, then this becomes zero. The inside part, the error becomes zero. If your prediction is same as the label y, then your error becomes zero. So what you are doing, you are not updating the weight. You are saying new is equals to old, right? This is zero. So new becomes same as the old. So there is some correction going on. Okay. So if prediction is incorrect, weights are adjusted, increase for underestimation and decrease for overestimation. Underestimation is 1 को 0 कर दिए, overestimation is 0 को 1 कर दिए. Okay. Right. So over here you see, we know how to obtain the equation of the line. So for a 2 dimension, for a higher dimension, we know the how to obtain the equation of the hyperplane. And now we can easily classify कि कौन से ग्रुप में कौन बिलोंग करता है. Okay. Is that all right? Then we'll proceed with something else. Is that all right? Okay. Now there can be some issues with this as well. Okay. We'll see the issues now. Okay. So you see, suppose these are the data. Circle है क्या यहाँ पे? Okay. And these are the data I have. And suppose the line which I have predicted is something like this. Okay. This is the line I have predicted. Okay. Now you see, there is some issue with this data set. Suppose there is a new, so what I have done is, currently I have completed modeling, I have tested it. Suppose I have tested it. We have not talked about testing, but suppose we have trained the data, tested the data, now we are trying to predict. So suppose this is our new data point. Now you tell me whether should we label it red or blue, or suppose this is the new data point, or suppose this is the new data point, this is the new data point. So whether it is red or blue, or suppose this is the new data point, or maybe this is the new data point, it is difficult to tell, right? If you label it as blue, it might be red. If you label it as red, it might be blue. So this strict classification कि blue ही होगा और red ही होगा, बीच में कुछ नहीं होगा, that is one issue we have. Maybe if we can say कि okay, for this point I am 95% sure it is blue, and for this point I can say I am 90% sure it is red, then it's better, right? Instead of just saying blue or red, it's better to say ki with probability ki if we have some probability with 60% assurance, I can say that it is red. So something like that, right? It will be better. Our model will be better. So that is what is being tackled by this soft threshold. So what happens is currently that step function looks like this. That step function looks like this. This is the step function we have, right? इसका नीचे हुआ तो 0, इसका ऊपर हुआ तो 1, right? So if this is the threshold, hard threshold, this is known as hard threshold. इसका नीचे हुआ then it is 0, इसका ऊपर हुआ then it is 1. This is known as hard threshold. We are trying to say कि it's not good. You see, when you are very close to this area, then your predictions might be questionable, right? When you are very close to this area. When you are far away from this area, then you are confident कि okay, we are very far away from this area, no ambiguity, we can just label it as either red or blue. But when you are very close to this area, then your prediction is questionable. What we do over there is we do logistic regression. So over there, so that is one more algorithm I'm talking about, right? So over here मैंने लिखा है कि नहीं, एक minute. Yeah, logistic regression. Okay. So what it does is, instead of plotting a very hard function, it plots a smooth function like this. Just a minute, it should be like this. Something like this again. It plots something like this. Okay. So what it does is it gives probability from 0 to 1. Suppose this is your new point. Suppose this is the new point you are saying. So what you do, you go up, you see whatever is the value over here. Suppose it is 0.7. So you can say with 70% probability, the label is 1. And if you are here, suppose, so you can just say with 30% probability, the label is red, or with 70% probability, the label is blue. Okay. So this is how that probability comes into picture. Instead of plotting that hard line, that indicator function, we can have a function which is curved, smooth function. Is that all right? Then I'll proceed further. Is that all right? Okay. So that function equation is something like this. Okay. You don't need to memorize. When you use Python, everything is inbuilt. Oh, so this is known as the logistic function. And W times X, when I write W times X, these are actually vectors written. So these are vectors written. So how it is written? So W is a vector and X is a vector, and we are doing cross product. So when I write W like this, it is actually, so I should have written it as, acha, there is a dot. So it is a dot product. So it is W naught, W1, W2, W3, Wn, and X is also a X1. So it starts with 1 actually. 1, X1, X2, X3, Xn. And when you multiply both, do a dot product for these vectors, so it will be W1, W0 times 1, so it is W0, W1 times X1, so it will be W1 X1, W2 times X2 will be a W2 X2, plus W3 times X3, plus dot 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 Wn times Xn. Okay, so we are just doing dot product over here, nothing new. So this dot products give me that equation, and you can just say less than equals to 0, greater than equals to 0, where we are talking about there. So this is that logistic function, and it gives you the probability. So when you say like this, so we can obtain that value, right? So we can obtain this value. We have seen how to obtain this value. We will put in this function 1 by 1 plus e to the power minus W dot X. So this W dot X is this. And whatever this value is, it will give a value between 0 and 1. Okay, it will give a value between 0 and 1, and this is the equation of that function. That whatever this equation is, this is that equation. Okay, and therefore we obtain a probability, and you can use that probability to say I am this % sure that this is the category of the new um, point. Is that all right? So this is known as soft threshold. Okay, I have you drawn over here. Is that all right? By the way, this is not correct. This should have been like this. Is that all right?
Shubham,
Yes.
please come back to the equation.
Yes.
Hmm. Probability of y is equal to 1 on the condition x has already occurred. Is it like that?
It is like
In that,
that. So
uh,
I'll just explain. So suppose you are getting this point, right? And this is 0.3. So you will say y is equals to 1 with probability 0.3. That means probability y is equals to 0 is equals to 0.7. So over here you see I have written 0.3 and not 0.7. So with 70% chance this point is a blue point, and with 30% chance this point is a red point. That is why it is written like that.
no, come back to that equation again. Okay. Is equal to 1 upon 1 upon 1 plus e raised to minus. Okay. So can I ask that why that for the soft threshold, particularly exponential function of the order 1 is chosen?
So actually there are alternate functions as well. So you can use alternate functions which follow this graph, this kind of graph. But it is seen that these logistic functions are good in predicting. So you can have other functions as well, which follows some similar kind of graph. Okay.
Okay.
But it has
Hmm.
seen that this function logistic function, and that is why the technique is known as logistic regression. This is logistic function, and the technique is known as logistic regression because it uses a logistic function, but you can use a different function. Nevertheless, it is seen that this function behaves better, performs better.
Okay.
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 All right. Support vector machine. Before going to support vector machine, um, okay, I can proceed to support vector machine. Now you see, this is another algorithm which helps in classification. What it does is, okay, so there are some issues with this not logistic regression. This is what? Perceptron model. You see over here we are just talking about linear functions. So we can have a linear plane. It can be 2D, it can be 3D, 4D, n dimension, but plane, right? What happens if your uh, data is something like this? How will you draw a plane? You will not be able to draw a plane that separates the um, two classes, right? You will not be able to draw a plane that separates the two classes. Okay, you can have like this also. So you can have red, more red over here, some blue over here. So you can just say this is my new boundary. So this can be more big data set. So these kind of things you will not be able to do using perceptron model. In that case, you have to use support vector machine. And what support vector machine does, I will not explain a lot because it requires 4 hours itself. Nevertheless, I'll tell you the idea and you can use it in 5 minutes in Python. You just have to import that support vector machine from some module and just use it. The idea is same. You have to divide your data set into two groups, a testing set and a training set. You train the data in one of the model. You specify which model you want to use, perceptron model, support vector machine, whatever model you have to specify it to Python. Python will do that algorithm inside in its code. It will build the model. You have to just call that model, give the new data set, and it will predict for you. So what is happening inside is not necessary to understand right now unless you're trying to understand machine learning more properly, or you're taking a course on machine learning. Okay, so what support vector machine is doing inside is not important right now. The idea I'll tell you. So you see, when we are doing this where is it? Okay, so when we are doing this kind of perceptron model, you see we can have multiple lines satisfying this category. We can have this line, we can have this line, we can have not this line, sorry, we can have this line, we can have this line. All lines satisfies the classification, and you can obtain any of the line using perceptron model. But again, I was talking to you like this for this problem only. This problem has some limitation. You see, if you have a dot over here, suppose this is the new data set, suppose this is the new data set you have, and you are using this model will predict that dot to be a red dot, but you can clearly see it seems that it is a blue dot, right? So support vector machines helps um, to remove these kind of issues. Okay, and I showed you one more issue. If you are going outside of linear models, then support vector machine will be helpful. So what support vector machine does, you see perceptron model just draws a line where it is able to classify the different points. Support vector machine takes into account the distance from the points. So I'll show you what it does. Suppose this is the line currently it is thinking to draw, support vector machine. Okay, what it will do is it will take the distance from this points. Okay, and it will try to minimize the distance such that that line is in between, something like that it tries to do. So if you draw a line like this, suppose this is the line, then support vector machine will turn it in a way that it tries to minimize the distance. Okay, so it is just like optimization. It has some function. It is trying to minimize the um, distance, summation of the distance from the points. It is very similar to that. The idea is very same. Okay, I'm not going into details, but the idea is this. And in such case, it will give you very good these boundaries. It may give you a very good boundary, something like this, which actually classifies the two with good regions of space where you might not miscategorize some points. Okay, so this is one thing support vector machine helps. It also helps in higher dimensions. So over here the boundary is of not one dimension, the boundary is of two dimensions. These boundary are two-dimensional boundaries, right? So using support vector machines, you can draw these kind of boundaries, which you'll not be able to do using perceptron model. Is that all right? Okay. So what we'll do is we'll take 5 minutes break and then we'll meet and start with regression. So we have completed classification. We will move to regression. And today we will not talk about Python coding. Next class we will see how to use these kind of ideas to actually do perform machine learning using Python. Over here we are just giving ideas of what machine learning is, how it is doing classification, how it is doing regression, and so on and so forth. Is that all right? Okay, so we will meet at 7:19. Okay, so I hope you are here. So regression we have talked about. So where we have outputs as continuous values, then we will use regression. Okay, and it is again supervised learning. So in classification you saw that it needed the labels, and that is how it was trying to improve the build the model as well, not improve, just build the model. So over here also it needs the values, that continuous values, and that is why it is also a supervised learning model. Okay. So examples. So this example I have taken from the Harvard University's lecture. You can just go and see there as well. It says that what are the advertising costs and the sales prediction of revenue from sales. So it says that it has only one input. It might not be true, but it says that it has only one input, the money spent on advertising, and the output is predicted revenue from the sales. So input is just x1 and y1. So I can just drop one. I can just say x comma y. What is x? X is the money spent in advertising. For example, 500 some unit, and the revenue can be suppose 600 or something like that, and so on and so forth. And you are trying to obtain a regression such that given a money spent value, you can just say this might be your revenue from the sales according to our model which we have built. Okay, so observed function f of, so what we are doing is over here we have a input x, we have a function which depends on this x, so it can be n dimensional function, it not be one dimension, and the output is actually f of x, which is y over here. So this takes input and it gives an output. We don't know the exact function, right? We don't know the exact function, we are trying to obtain that function, which is known as the hypothesis function. Over there also, when we were doing classification, we didn't knew what is the exact function. That is why we are trying to build that function. When we are saying perceptron model, that equation was a was that function which was trying to tell you ki what should be the output, given the input what should be the output, right? So over here as well, given an input, we don't know the exact function, we are trying to get this h. This is a hypothesis function. We are saying this is what my prediction is. We will obtain this function, we will not know what this function is, and that is how we obtain data. We don't know the exact relationship between input and output, we're trying to obtain that relationship using machine learning. Okay, line that approximates function x to predict the revenue. Okay, so this is one example I have taken over here. This is the regression line which is plotted for this small data sets, and if you have obtained this line you can just do predictions. If you have a new data for this input, you can just go to this line, see what is the output, and you can just say this is the output for this input. Okay, so this is that line, this is the hypothesis line. We don't exactly know what is the input, the exact function. Okay, so for classification, so loss function. So if you remember, in the last class I was telling you that machine learning uses optimization ideas. So we will see over here how it uses the optimization ideas. So you see, we have the points, the training data we have. Now what it will do is it will obtain what is the loss. So for classification also it uses optimization. I'll just show you for regression analysis. So you see, you can have a loss function which says what is the actual value and what is the predicted value, and you can take the difference, and you can take the modulus. Why modulus? Because we will sum it for all, so it is sum actually. Okay, so what it is so you can just take sum of, so suppose I am saying actual is y and predicted is h of x. So we will say sum of all these over all the points in the training set. So when you sum this, so you see what is it? The correct y is this. This is the correct y, and my line is actually predicting this. This is what my line is predicting, h of x. So my line is predicting a little less. It is visible for the other point. So you see, for this input, For this input, the actual y is this. Actually, y should be this, but my model is predicting this, right? My model is predicting this. So this is actually the error. And the total error, the total loss is sum over all the points, point 1, point 2, point 3, point 4, point 5, sum over all the points. So this sum is over all the points. So you can either take modulus. Why modulus? Because the positive side and the negative side should not cancel each other. That's why we are taking modulus. Or you can take square. I guess you have heard mean square error, MSE, mean square error. So this is the mean square error. Okay. So this is known as the L1 function, loss 1 function. This is known as the loss 2 function. And what optimization, how optimization is used? We will try to minimize this function. We will try to minimize this function. So the problem, optimization problem is minimize sum over all the points. So I is equals to, I belongs to the n. So I'll say n is the set of the points. I belongs to n. yi minus hxi whole square, not whole square over here, whole square. So you see, this is that function. This is the objective function. We will try to minimize this objective function, right? So this is an optimization problem. Is that clear? When you minimize this objective function, this equation will be obtained, right? You see, h of xi is what? H of xi is actually the equation of the line. So that will be the constraint. That will be the constraint. Is that all right? When you minimize this line, you obtain that. When you minimize this function, you obtain this line. You can have multiple lines. You can have this line, you can have this line, you can have this line. The best line which minimizes this function is the regression line, is that line. Okay. Right. So we have the loss function. Similarly, we can do this for, so over here we have the loss function for, yes, yes.
Mm, How exactly summation means the mean square error summation function? Our aim is to minimize the error. Ideally, it should be zero.
Yes, ideally should be zero.
So summation cannot be. I think summation cannot be equal to zero. Individual case has the error value that shall be equal to zero.
Why?
Shall it be like this?
If individually everything is zero, the sum will be zero, right?
No. For example, say example 1, 2, 3, 4, 3, 4, 5.
So
Out
for
fi- out
for
of
this
five
problem,
samples, we get
just
correct samples and one incorrect sample.
right. In
In
that case, error will never be zero.
ha.
So I'm saying,
So
suppose for this, just a minute, for this problem, it seems that you will not be able to draw a line that passes through all the points. Suppose you have a data like this, where you can draw a line which passes through the data.
yes,
In that case, the mean
correct.
error will be zero, but it never
Yeah.
happens. That is why we are trying to minimize this error. We are not saying this error will be zero. We are
We
saying we are,
must minimize the error, no doubt. But each summation really necessary?
yes, we are trying to minimize. So what will happen is, if you're not doing the summation, suppose you are just saying minimize the error for this point, the line will pass from this point. So this line is also minimizing the error for this point. This line is also minimizing the error for this point. This line is also minimizing the error for this point, right? For this point, the error is zero for all the lines. But you
Hmm.
see, this line has a minimum error from this, but the error increases as you go from this line, and the other lines, right? So you have to minimize summation of the errors for all the points.
Okay. Hmm.
Okay, is that clear?
Yeah.
Okay. So we can have a same kind of equation for classification loss also. So you can say if actual is equals to predicted, the loss is 0. Otherwise, the loss is 1. You can just sum the errors and you can have a similar function for that as well. So you see this L1 loss, that is actually a linear function. It increases. So what it does is, so for L2 loss actually penalizes the function, penalizes the points which are far away. So what I mean is, if the error is large for a point, it tries to minimize, it tries to penalize it more because it is doing square. So higher will be the distance from the actual, higher will be the penalty because it is doing square. So 2 square is 4, 3 square is 9, 4 square is 16, 5 square is 25. So higher is the error, higher is the penalty. Therefore, it grows so this is actually a parabola, quadratic function, right? This is a linear function. So L2, so you have to see whether L1 is useful for you or whether L2 is useful for you. If your whatever you are trying to model, if going far away from the actual value is very detrimental for you, it's not good for you, you use L2 function to minimize L2 function. Otherwise you can use just L1 function. Okay, so you have to choose which function you are trying to minimize, right? Now overfit.
I have one doubt.
Yes.
Uh, will it be always good to consider like this higher order, or sometime means can we may sacrifice at some point, means at other points, no?
Which points?
Means wherever the max, if we are trying to minimize the maximum error, then will it be the best fit?
Minimize the maximum error. Okay, so over
Mm.
here you are saying I will minimize the maximum error. So what will happen is, it will do like this. I'll just show you what will happen if you try to minimize the maximum error. So suppose the function you are saying is minimize maximum of yi minus xi. This function you are trying to minimize. So suppose there was one more point over here, a 1 2
No,
3
not like this. I'm telling this higher order you are doing means square and so on. Correct.
right.
They are automatically wherever the error is more, there it is focusing. Correct. Means if somewhere error is 1, somewhere error is 5, so it will be minimizing that 5 square. Means x square will be, that is the error whose highest value means very high value will be tried to give the main focus. Am I
Right,
correct?
right. So it depends
So
upon what your objective is. If you it is something where you are so where you saw that there might not be any outliers, you know the outliers will be very less, then using this square is better. But if you know that your data is has a lot of outliers, then in that case going for this L1 function will be better, right?
yeah, that is
So it depends
the
upon your
square fitting will be much difficult, maybe difficult, no?
right.
If okay, thank
Okay.
you.
So overfitting, you see, currently we are only talking about linear regression, right? So these are all linear regression. We are plotting a single line. You can have polynomial regression as well. So if you come back when we are talking about the algorithms to solve this kind of problems, just a minute. Over here we saw linear regression, we saw also polynomial regression. So I'll give you an idea of how polynomial regression is done just in a minute. Then I'll move forward maybe. So over here, how to do polynomial regression. So you see over here, I am saying this is one input and one output, right? One input, one output. So what you do is you create one more feature. So you have X and Y, right? You have X and Y, and you are plotting a linear line. You're saying X is a function of Y. What you do is you create one more feature X square, and you say y is a function of x comma x square. You are doing linear regression, but you are considering a quadratic function. So it is actually a polynomial regression. If you try to do more higher order, so if you say I will consider x cube as well, so you can say y is a function of x comma x square comma x cube. So in these cases your line might not be straight, your mind line can be like this as well, your line can be like this as well. Okay, so higher the order, so I don't know what should be the curves of the line, but you can have higher order curves as well. Instead of just a linear line, you can have higher order curves using this idea. We are using the idea of linear regression, but doing polynomial regression because we are making the feature as square, cube, and so on and so forth. Okay. Any doubt? Is it clear? Okay. So yeah, so now the question comes of overfitting. You see, I'll just erase this again. So suppose we are doing polynomial regression. Suppose for the time we are doing polynomial regression and we obtain this line. Suppose we obtain this line. So do you think this is a good regression curve? It is not, right? We are overfitting the data. We have minimized the error to 0. Now what happens is when you do predictions, it will give bad results. If it will give it, so you see when we are starting, we were talking about bad results. Even if the model is very good, you may have bad results. This is how, this is overfitting. So now when you predict, suppose this is your prediction, so earlier you would have predicted this, but now you will predict this due to overfitting. So overfitting, you have to ensure that you're not overfitting your data. So suppose there are more points, and your curve become like this. Suppose there are more points, right? So in that case your regression line will become something like this. So these are very things to be taken care of. So this is known as overfitting. How can you prevent overfitting? When you minimize loss, you also consider complexity. So you don't go very high, you try to remain linear or quadratic. You can check, you can say I will do linear, I will do quadratic, I will go to the power 3 4 5 6. And since you have training set and testing set, you can see how your errors in the testing set changes. So what I'm saying is you have divided your data set into two part, training and testing, right? So what you do is you check regression for order 1, order 2, order 3, order 4, and so on and so forth, 5, 6, 7, and till 10 you are doing. Suppose you're 10 you are doing. So for each of these, you see what is the error for the testing set, right? For each of this. And you pick one which is having less error in the testing set. In that case, you will be sure, okay, we are not overfitting. You will see what happens is first the error will decrease for the testing set, but again the error will increase. So what it is doing is it is first approximating the function very nicely, but since you are overfitting the data more and more, the error in the testing set becomes more. Okay, is it clear or should I explain more? So the idea is to check कि first order work कर रहा है कि second order work कर रहा है, third order work कर रहा है. You have to check for each of those. How will you check? You have a testing set. You will use the testing set to check which is working better, right? Is it clear? Okay. Okay, so overfitting is done. Yeah, so we have, so now how will we solve this? We can either do regularization or cross validation. So I have talked about regularization. When you are talking about the loss function, you take into account the complexity of the problem. That is known as regularization. I'm not going into detail. These are very big topics. Okay. So I've talked about regularization. Another is cross validation. So you see, when you have data and you want more for training, right? You need more. So you are saying, suppose 100 data sets I have, I will use 90 for training and 10 for testing. This 10 may be very less. In that case, you can do cross validation. How what does it do? So you see, for this 100 data sets, you can divide it into groups of 10, right? You can have groups of 10. 1 2 3 4 5 6 7 8. Right? Now what you do is you pick 9 of them and make it the training set and use this as the testing set. First case. For the second case, pick the next 9 of them and use one as the testing set. For the third case, you again do the same but leave out the other. So you will have multiple testing set and multiple training sets and you use those. So k-fold cross validation is you are trying to split the data into k subsets, train on k minus 1 folds and test on the remaining fold, repeat the k times and average out the result. The advantage is it uses all the data for training and testing without overlap. And this will help in reducing the um, overfitting as well, because you are using whole data. Instead of leaving out some of the data, you are using whole data for doing training as well as for doing testing. So the idea is to hold out some of the data, but do testing in those data as well in the next iteration, right? So this is um, what is cross validation. Is it clear?
Shubham,
Yes.
so what do we achieve with the cross validation? I did the cross validation in a particular case. There are we are making group of 10, and out of 10 groups, 9 are used for sorry, validation. 10 are used for testing. Correct.
Right. So
So
what the advantage?
in this case, we will repeat the experiment for 10 times. Correct.
Right. So what is the
And
advantage
we
of?
obtain 10 different results.
Yes.
Correct. Now we have a set of 10 results. Next is what?
So those again, this average of result is a compound statement which has a method to how to combine those datas. And in Python, you will just have to write one line. It will do it for you. Okay.
Okay, okay.
Now, what is the advantage of cross validation is you have more data to test on. You see earlier you have only one part of the data to test. Now you can test in the whole data set in different groups, right? But you can test in the whole data set. So you have more data set to test on.
Okay. Yes.
So this is the end of this lecture. I have written some code to explain, but it will take some time. Therefore, I don't think it is wise to start that now. So what I should do is I should end the class today. Okay. Now one announcement. Our next class,
Please show me the references that you used for.
I will upload this slides.
Yeah, yeah. Okay, okay, okay.
So what I'm saying is that, Acha, by the way, in this reference, I have mistakenly put this. It shouldn't have been there. So the first reference is not used. Okay. So that first reference is for the previous uh, module. It is not used in this module. So what I'm saying is our next class will be after 15th. So 15th also I'll not be able to take class. I am going to IIT Bombay tomorrow and I will return on 15th. 15th is a Sunday. So after that we will have 3 weeks. From 16 to 31st there are not 3 weeks, less than 3 weeks. And I will need more, at least 4 classes, 3 to 4 classes. So my plan is to finish before 31st December. I will try to do that. So our next class will be on maybe 17th December. I will inform everyone. I will inform in the WhatsApp group as well. And in during that time, I would request you to do assignment 4 as well as work on your project. Okay. Any doubts or concerns?
So this 17th you will be taking the last class. After that, whatever the classes you will be taking, the recording will be available.
Yes,
Correct.
yes, recording will always be available.
Means, that will be available even after means 31st December also.
Yes, yes, recording I will not remove.
Okay. Because after 17th, I shall not be able to attend the classes.
Okay, no problem.
Thank you onwards.